Hello guys, welcome back to Iconic Blogger. So today I'm going to solve a numerical on data encryption standards. The pre-required knowledge for this are concepts of encryption and decryption, Feistel data block cipher, and basic of DES. Problem I am going to use to solve DES is states this problem provides a numerical example of encryption using a one-round version of DES. We start with the same bit pattern for the key K and plain text, namely hexadecimal notation 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and binary notations are given, and it asks to 9 questions which are based on it. So we are going to step by step finding out all the answers by understanding how DES works. And why I choose to solve this question is because I got one assignment from my teacher and I was unable to find the answer, although I found answer on Google, but they all are demanding to pay $7 to $10 for it. So I am uploading the solution for this problem free of cost, so that anyone wants the solution of this problem can find it here. And if want the written text, then they can go to my blog, that is cscbysakshi.blogspot.com, and I will upload the link in my description. To solve this problem, some basic concepts are need to be cleared. Some of them are: you should have the knowledge of encryption and decryption, you should know what is Feistel block ciphers, and you should know how to operate DES. I will surely make videos on DES basics and encryption and decryption. Till then, let us continue with this problem. So I will be solving step by step each and every step. So let us start. As we know that M is given, that is plain text, and M is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So by observing this, you can say that M is an hexadecimal format. So we will rewrite this M in binary format and we will get a 64-bit block of text. So I have already converted this hexadecimal base format of M into binary format. Let us see how to convert hexadecimal to binary. In hexadecimal, F is equal to 15. We will use 8421 configuration, that is put 1 under the digit you want to use. So for 15 we have to add 8 plus 4 plus 2 plus 1. So we will put 1 1 1 under 8421. So the binary code for F is equal to 15 is equal to 1111. So this is how all the digits in M that are in hexadecimal format are converted into the binary format. Now what we will do, we will split this M into two equal parts, that is in left and right parts. The L consists of first 32-bit of M and R consists of last 32-bit of M. The first bit of M is 0 and the last bit is 1. We read from left to right, and DES operates on 64-bit block. DES uses a key size of 56 bits, and one more thing that you should notice here is that the L is written in the forms of nibble, that is group of 4 bits at a time. So to total 8 nibbles are used to represent L and 8 nibbles are used to represent R. As I said earlier that DES uses a key size of 56 bits. The keys are actually stored as being 64-bit longs, but every 8th bit in the key is not used. That is, bits number 8, 16, 24, 32, 40, 48, 56 and 64 are not going to be used. So let us take a key K of hexadecimal format. K is equal to 133457799 BB CD EF 1. So we will convert this key again into hexadecimal format using the same conversion using 8421 formula, and then the key K is rewritten in the binary format. So the first step we are going to do in DES is creating 16 subkeys, each of which is 48-bit long. So the question is, why to use 16 subkeys rather than using the actual key? DES uses the Feistel block cipher, and Feistel block cipher operates in blocks. For every block it uses a different key. So here we are going to create 16 blocks and 16 subkeys, and each subkey will have a part of the actual key. So these 16 subkeys are going to be 48-bit long, and the 64-bit is permutated according to the following table PC1. This table will be already provided. What it says, since the first entry in the table is 57, this means that the 57th bit of the original key K becomes the first bit of the permutated key K plus. The 49th bit of the original key becomes the second bit of permuted key. The fourth bit of the original key is the last bit of the permuted key. We can see PC1 is 7 by 8 cross matrix, that it will create 56-bit key. We are going to ignore every 8th bit. For that, this is our key in binary format. We will convert the first 8 bits. That we will see at the 57th position it is 1 in the key, so we will take 1 for K plus key. Similarly, for the second bit of K plus, it is 49 in PC1. At the 49th position it is again 1, so we will write 1. Similarly, we will see others for 41, 33, 25, 17 and 9th position. So the first block of K plus key is 11110000. It is 7 bit, and similarly we will convert rest of the K to K plus. This K plus is the permuted key, and now we will split this key into left and right halves of C0 and D0, where each half has 28 bits. From the permuted key K plus, we get C0 and D0. In C0, we will use the first 7 bits group, and in D0, we will use next or the last 4 groups of 7 bits. So our C0 and D0 are defined. Now we can use them to create the next 16 blocks of Cn and Dn. Now we will derive the values of Cn and Dn by putting n is equal to greater than equal to 1 and less than equal to 16. Since we need the values of Cn and Dn to create our keys from K1 to K16, so we have to find out these values. And to do so, we will use the shifting methods. You have done shifting. What we do, we will do either we will do only left shift, and for that either we will do one left shift or we will do two left shift on the C0 and D0, and this is how we are going to make our Cn to Dn values. I have shown the iteration numbers, that is for n is equal to 1 to 16, and the number of shift we are going to make on C0 D0. And for making C1 we will use the values of C0 D0, and to make C2 D2 we will use C1 D1. Similarly, for to calculate the values of C16 D16 we will use the values of C15 and D15. For example, if you want to calculate the values of C3 and D3, they will be obtained from C2 and D2 by doing a 2 left shift, and C16 and D16s are obtained from C15 and D15 respectively by 1 left shift. So the table or the iteration number shown before will be used to make the shift. So this is the original pair of C0 and D0 we have obtained, and now what we will do, we will apply one shift to calculate the values of C1 and D1. Similarly, to obtain the values of C2 and D2, we will apply one left shift on C1 and D1. Now to obtain the values of C3 and D3, we are going to apply two left shift. That is, we will move the first 2 bits of C2 to last of the C3, and we will start C3 from third bit of C2. Similarly, for D3 we will do same. We will move the first 2 bits of D2 to last of the D3, and the D3 will start from the third bit of D2. So in the same manner, by looking that iteration table for 1 or 2 left shift, I have created all these Cn to C and Dn values for n is equal to and greater than 1 and less than equal to 16. So let's have a quick look on all these values. So this is how all the values, these are all the values which are already calculated. So we now from key Kn for n is equal to greater than equal to 1 and less than equal to 16 by applying the following permutation table to each of the concatenated pair Cn Dn Each pair has 56 bit, but PC2 only use 48 bit. So we will use this PC2. Therefore, the first bit of KN is the 14th bit of CNDN. Second is 17th and so on, ending with 32th bit of CNDN as the 48th bit. The first question in the numerical problem was to derive K1, that is the first round key. So now we can calculate the first round key using the C1 and D1 values. We will just simply put these key values together of C1 and D1, and we will apply the permutation from PC2 table, which is already shown to you, and it will become like this. And when you are writing the values, we will write them in the form of 6 bits at a time. Similarly, the values of C2 and D2 can be used to calculate the value of K2, and so on. You can calculate the all keys using the values of C and Dn up to C16, D16 to calculate the value of K16. So let's have a quick look on all the keys so that you can rewrite them. These are all the keys. So the next step here is to encode each bit 64-bit block of data. There is an initial permutation IP of the 64 bits of the message data M. This rearranges the bits according to the following table already given. This is the IP table. You will already have this table, and what you are going to do will permutate the bits according to this IP table. That is, the 58th bit of the M will be the first bit of the IP, and the 50th bit of the M will be the second bit of IP, and the 7th bit of the M is the last bit of the IP. I have already shown you how to permutate using a table, so we will apply the initial permutation to block M. After applying this initial permutation, we will get the value of IP. So the value of IP has been calculated. Now we can solve the second question in the problem, that was to derive L0 and R0. For that, we will divide IP, that is a permuted block IP, into a left half of L0 of 32 bit and a right half of R0 of 32 bits. The values of L0 and R0 are written here, which are derived from IP by splitting it into 32 bits. We now proceed through 16 iteration from 1 is less than equal to n is less than equal to 16 using a function f, which operate on two blocks, a data block of 32 bits and a key kn of 48 bits to produce a block of 32 bits. Let this sign, that is plus inside a circle, denote the XOR addition, that is bit by bit addition, and then modulo 2. Then for n going from 1 to 16, we will calculate all these blocks. So now we will calculate all the values of Ln and Rn for n is equal to 1 to 16, and to do so we will use Ln is equal to Rn minus 1, that is we will use the value of previous block of Rn minus 1 for the new value of Ln, and to calculate the value of Rn we will use the XOR function using Ln minus 1 value with XORed with the function Rn minus 1 and key kn. Let me take an example. For example, if you want to calculate the value of L4, then for L4 you will write the value of R3 directly, and to calculate the value of R4 you will take L3 and XOR it with the function R3 and K3. So this will result in a final block from n is equal to 16 of L16 R16, that is in each iteration we take the right 32 bits of the previous result and make them the left 32 bit of the current step. For the right 32 bit in the current step, we XOR the left 32 bit of the previous block with the calculation f. For n equal to 1, we will have k1 is equal to this much, L1 is equal to R0, and for R0 we will calculate it using L0 XORed with the function R0 and k1. So to calculate f, we first expand each block Rn minus 1 from 32 bit to 48 bit, and this is done by using a selection table that repeats some of the bits in Rn minus 1. This selection table of function e, thus e Rn minus 1 has a 32 bit input and a 48 bit output block. So this is already told you how to use the table to expand the values, so you can easily do that. So let e be such that the 48 bit of its output written as 8 block of 6 each. To do so, the first 3 bits of E, Rn minus 1 are the bits in position 32, 1, 2 of Rn minus 1, while the last two bits of Rn minus 1 are the bits of position 32 and 1. Similarly, you will calculate all the values of expanded R, and the next question in the problem was to expand R0 to get ER0, where E is the expansion function of table 3.2, and this is the table which I have already shown you. So we will calculate ER0 from R0 as follow. So we have the value of R0 and we will expand it using the previous table. This is how we are going to do. We will put 32th bit here, and then we will calculate 1 2 3, and similarly we are just going to expand this 4s to the 6 values. And next in the F calculation, we XOR the output of Rn minus 1 with key Kn. This is the basic formula in the rectangle, Kn plus Rn minus 1. And the next question in the problem to calculate was to calculate the value A, where A is equal to ER0 plus K1. So basically we are going to calculate a XORed function of the expanded R0, that is 32 is bit of R0 are expanded to 48 bit using the expansion table, and only then we can XOR it with the key, and our key is a 48 bit length, so we need R0 to be 48 bit length. That's why we have expanded it using the E table. So these are the values of K1 and R0 after expansion, and we will XOR them. And for XOR you should know 0 0 is equal to 0 and 1 1 is also 0. Only we will put 1 when either of the input is 1, that is either 0 1 or 1 0. Then we will put the XOR output as 1. So this is how this A value is calculated. Now the next question is to group the 48 bit result of T into sets of 6 bits and evaluate the corresponding S box substitution. So we have not yet finished the calculating function F, and we have expanded R and minus from 32 bit to 48 bits using the selection table and XORed the result with key Kn. We now have 48 bits or 8 groups of 6 bits. So these 8 groups of 6 bits, each group is denoted using B, that is B1 to B8, and the whole group will be called as S. So we will use these blocks to calculate the values of S boxes. Thus the 8 groups are used as address in the tables called S boxes. Each group of 6 bits will give us an address in a different S box. Located at the address will be a 4-bit number. This 4-bit number will replace the original 6 bits. The net result is that the 8 groups of 6 bits are transformed into 8 groups of 4 bits, and we write the previous result, which is 48 bit, in the form of Kn plus Ern minus 1, that is equal to B1, B2, so on to B8, and each Bi is a group of 6 bits we now calculate. So we will calculate this S boxes using S1 B1, S2 B2, so on to S8 B8, where Si Bi refers to the output of the ith box. To repeat each of the function S1 to S8, take a 6-bit block as follows, and it is explained here how we will calculate the S1. And to calculate the S1, you can see that I have numbered the rows from 0 to 3, that are 4 rows, and the columns from 0 to 15, that are 16 columns. So if S1 is a function defined in this table and B is a block of 6 bits, then S1B is determined as follow. The first and last bit of the B, B is a 6 bit. The first and last bit of the B will represent in base 2 as a binary digit ranging from 0 to 3, that is either 0 0 to 1 1. So we can go from 0 1 to 3. So this is the number. And for the rows, let us have number Bi. The middle 4-bit B represent the base 2 number in the decimal from range 0 to 15. So we are representing it in the column form. So let it be Z. The binary values in column will range from 0 0 0 to 1 1 1 1. That is 8 4 2 1 formula again. So look up in the table, the number in the ith row and the jth column is a number in the range 0 to 15 and is uniquely represented by a 4-bit block. That block is the output S1B of S1 with the input B. For example, for input block B is equal to 0 1 1 0 1 1, the first bit is 0 and the last bit is 1. So it gives us 0 1. So as the row with this implies that the row is 1 and the middle 4 bits are 1101, and this is binary equivalent of the decimal 13. So the column is column number 13. In row 1 and column 13 appears 5, and 5 in binary bit is written as 0101. So the output here is 0101. So S1 into the B block for value 011011 will be equal to 0101. The table defines the function S1 to S8 are as follow. So you can have this look of all the tables. I have already calculated these tables and written here. You can copy them, or you can also take them from my blog, that is cscbysakshi.blogspot.com. So these are all the blogs which will you already have, and you will use these blogs to calculate the values accordingly for the addresses in the binary bit of 8421 coding for S1 and B1 values. So the next question in our problem was to concatenate the results of E to get a 32-bit result B. So what we will do, we will concatenate the results using K1 E R0, that is S1 B1 S2 B2 so on to S8 B8, and it is named as B. So our values after all these blocks are derived is these are the all values, that is for S1 B1 it is 0101 and S2 B2 it is 1100. Similarly for S8 B8 it is 0111. So the B value is the concatenation of these values, and since these are 4 bits, so 84 is equal to 32. So this is a 32-bit result B. The final stage, the calculation of F, is to do a permutation P of the S box output to obtain a final value of F. So F will be is equal to the permutation of P, and to do this permutation we will use the following P table, which will again tell you how to arrange the bits. The next question in our problem is to apply the permutation to get PB, and to do so the permutation P is defined in the following table: P yielding a 32-bit output from a 32-bit input by permutating the bits in the input block. So the B is the input and we will permutate them according to this, that is for B the value of B 16th bit of the B will be the first bit after permutation, and the 25th bit of the B will be the last bit of the permutation after permutation. So we will calculate the value of next we will calculate the value of R1, that is PB XORed with L0. From the output of the 8 S boxes we have already calculated the value B, and after applying the previous P table we have calculated the F function PB, which is something like this. And now we will calculate the value of R1, that is L0 plus F R0 K1. So we will again XOR these values. Why we have done this all things? Because our key was 48-bit, R0 was 32-bit, we converted R0 to 48-bit, then again we converted it in address form of S boxes to convert it into 32 bits so that we can XOR it with L0. So now we can XOR these 32 bits, that is L0 and PB, and you know how to XOR. This is the result of R1. In the next round we will have L2 is equal to R1, which is the block we just calculated, and then we calculate R2 as L1 plus function R1 K2, and so on for 16 rounds. At the end of the 16th round we have the blocks L16 and R16. We then inverse the order of two blocks, that is we will put R block first and then L block, R16 L16, and apply a final permutation, that is IP inverse, which is also defined here, and you by the time has known how to apply the permutation. We will combine the values of R16 and L16, but putting R16 first, and the first 48th bit of the output of R16 L16 will be the first bit of IP inverse, and 8th bit of R16 L16 will be the second bit of the IP inverse, and similarly we will do this for. And if we process all the 16 block using the method defined previously, we get on the 16th round, and L16 and R16, these are the values of L16 and R16. We will reverse the order of these two blocks and finally apply the inverse of that table, that is IP inverse, and this is the value we will get after the inversion. And the hexadecimal format of this IP inverse is 85E813540F0AB405, and this is what we required for our last question, that was to write down the cipher text. So our encrypted form of M, that is 012345678 A B C D E F, is 85E813540F0AB405. So this was the whole solution for DES. Hope you have understood it and you know by the time how to do this all the steps. If there is some misunderstanding, please do refer my blog, that is CSC by Sakshi blogspot.com, and I will give the link into description also. Thank you for watching.